Question: the three cranks of a three-cylinder locomotive. Right now, the cylinder number is 3. Are all on the same axle and are set at 120 degree. Right. So now we have 3 cylinders, each of it at 120 degree. The pitch of the cylinder is 1 meter, and the stroke of each piston is 0.6 meter. The reciprocating masses are 300 kg for inside cylinder and 260 kg for each outside cylinder. Right, so we have 3 cylinders, so 1 inside cylinder and 2 outside cylinders. And the planes of rotation of the balance masses are 0.8 meter from the inside crank. Right, now we have the length of the revolving mass as well. If 40% of the reciprocating parts are to be balanced, right? So now we have to balance only 40% of the reciprocating parts, right? Find first the magnitude and the position of the balancing masses required at a radius of 0.6 meter, right? So now we have to add the balancing masses at 0.6 meter. And second, the hammer blow per wheel when the axle makes 6 rotation per second, RPS, right? So this is our question. Now we'll see how to solve it, right? So it's given the angles, right? So now we have 3 cylinders, each of is at 120 degree, right? So now we have 3 angles, each of is at 120 degree. All right. And stroke length. Stroke length is given 0.6 meter, right? So 3 cylinders, each of is at stroke length 0.6 meter. And we know if the stroke length is 0.6 meter, the radius of the relevant crank is half of the stroke length, that is 0.3 meter, right? And the masses, reciprocating masses of inside cylinder is 300 kilograms. So we'll consider it as M1, which is 300 kilograms. And of the outside cylinder, that is 260 kilogram. MO, that is 260 kilogram. Mass outside 260, similarly mass inside 300 kilogram, right? And we have to balance only 40% of the reciprocating parts. So C is 40%, right? That is 0.4. And the question is, magnitude and systems of balancing masses required at a radius of 0.6 meter. So now we are supposed to add the balancing masses at 0.6 meter. B1 is equal to B2 is equal to 0.6 meter. And the radius of, the RPM is given, which is 6 RPS rotation per second, right? So if it is 6 RPS, then we have to multiply it with 2 pi. So which will give you 37.7 radians per second. Okay, so this is the given data, right? Now we'll see how we are going to solve it. Okay. Since 40% of the reciprocating masses are to be balanced, right? So in the question it's given only 40% is to be balanced. So now we have 300 kilogram for the inside cylinder and 260 kilogram for outside cylinder. So among this weight, only 40% is to be balanced. So now we'll calculate. So 0.4 into 260, that is 104 kilogram for the outside cylinder, and 0.4 into 300 kilogram, that is 120 kilogram for inside cylinder. So now we are going to balance only 104 kilogram for outside cylinder and 120 kilogram for inside cylinder, right? Only 40% of the reciprocating parts are to be balanced. We'll start. Magnitude and position of the balancing masses. We'll consider B1 and B2 are the two balancing masses, right, in kilograms. And theta 1 and theta 2 are the angular positions of these two balancing masses, right, B1 and B2 from crank A. Okay. So we'll start with these diagrams, right? So first, position of the planes. We mentioned it's 3-cylinder engine, right? So we have 3 cylinders A, B, and C, right? And the pitch length is 1 meter, right? So the length or distance between the cylinder is 1 meter. Okay. And it's given, and the planes of rotation of the balance masses are 0.8 meter from the inside edge, right? So that is 0.8 meter from the inside edge, right? So we'll consider any one of the plane as the reference plane. I'll consider this one, right? So from this side it's negative, and for this side it's positive, right? You can take either way. All right. So this is the position of the planes. Now we'll mark the position of the cranks. Right, so we mentioned it's in the question it's given. Three cylinders, each of it's at 120 degrees. So we have cylinder A1, 2, and 3, A, B, C. Each of them are at 120 degree, right? And also we have two balancing masses. We don't know, right? We'll consider as B1 and B2 at theta 1 and theta 2 angles, right? And the length of them is 0.6 meter. And also the length of the three unbalanced masses are 0.3 meter. So this diagram is for the position of the cranks, right? This one is for position of the planes. Okay. So now we'll decide which polygon to draw first, whether it's coupled polygon or force polygon. For that we need to first fill the table, right? So first we'll fill the table. We have planes A, B, C. That's a three unbalanced masses, and balancing masses 1 and 2, right? Two balancing masses and three unbalanced masses. And I'll consider the unbalanced mass 1 as the reference plane. Okay. So we'll fill the table. First one, mass per kilogram. Mass or kilogram, right? Mass in kilogram. So here we are going to put the mass which is need to be balanced, right? Not the final, not the full mass, right? So the mass need to be balanced. For outside cylinder is 104 kilogram for A and C, and 120 kilogram for inside cylinder B, right? So that we have already calculated here, right? For A and C it is 104 kilogram. For B it is 120 kilogram. Why? It's only 40% of the final mass, right? So that we know. The balancing masses B1 and B2, we don't know, that we have to find, right? And then the radius of rotation for the unbalanced masses, it's 0.3 meter, right? So A, B, C, it's 0.3 meter. And the balancing masses are to be placed at 0.6 meter. Okay. And now centrifugal force we have to calculate. So we'll usually multiply mass with radius and we'll divide it by omega squared, right? Because we don't need to complex the things, right? So we'll multiply mass with radius divided by omega squared. So 104 into 0.3, 31.2. Then B1 into 0.6, that is 0.6 B1. 120 into 0.3, 36. B2 into 0.6, that is 0.6 B2. 104 into 0.3, that is 31.2, right? So this is the force, right? Force which you have calculated. So we'll use this data to draw the force polygon, right? Now the distance from the planes, distance from the reference plane. So I will consider 1 as a reference plane. So that is 0. From reference plane to plane A, that is 0.2 meter according to this diagram, right? So from reference plane 1 to plane A, that is 1 meter minus 0.8 meter, that is 0.2 meter. Okay. From reference plane to point B, that is 0.8 meter. Okay. From reference plane to balancing mass 2, that is 0.8 plus 0.8, 1.6 meter. Right. From reference plane to unbalanced mass C, that is 1 meter plus 0.8 meter, that is 1.8 meter. Okay. So we fill these details in the table. Okay. So from reference plane to A, that is 0.2, but that's on the other side of the reference plane. That's why I consider it as minus 0.2. Then from reference plane to B, 0.8, reference plane to unbalanced balancing mass 2, that is 1.6, and reference plane to unbalanced mass C, that is 1.8. Okay. So this is the distance from the reference plane. Okay. Now we'll calculate the couple. So we know to calculate the couple, we'll multiply this with this, right? So column number distance from plane into force. So we'll multiply these two. So couple what we have divided by, and also we'll divide it by omega square, right? Why? Because we don't need to have much complex numbers here, right? If we use omega square here, then we have to multiply it by 31 point something, right? So we have to multiply it with the 37.7 whole square. We don't need that, right? So we'll have this as simple as possible. All right. So by multiplying this with this, we have minus 6.24. 0 into 0.6 B1, that is 0. 0.8 into 36, that is 28.8. 1.6 into 0.6 B2, that is 0.96 B2. 1.8 into 31.2, that is 56.16, right? So these data we will use to draw the coupled polygon, and this data we will use to draw the force polygon, right? Alright. So now we'll draw any one of the polygon first. So we'll decide which one to draw first, right? So if you consider the coupled polygon, we have only one unknown, that is B2. But if you consider the forced polygon, we have two unknowns, B1 and B2. So what we'll do, we'll start with the coupled polygon because we have only one unknown, which will be easy to draw, right? So we'll start. Okay. So first, in order we'll go, right? So O2, I'm starting from A. So O to A, right? OA, according to table, that is minus 6.24, right? And also you have to draw according to the scale, right? So whatever you are drawing in theory of machines, you have to draw according to the scale. So first one, you can select any suitable scale. Okay. So here, from reference plane to A, that is 6.24, the coupled. Okay, coupled polygon 6.24. OA is this way, but I am drawing the other way because it's negative, right? The value is negative. Because if you see, OA is this way, but I am drawing OA this way. Why? Because that is negative minus 6.24, right? So that's why it's this way. And then we have the next 0.64, then 0. We don't need to draw it. Then we have 28.8. Okay. So from O to B in this direction, that is 120 with this one. Okay, 120 with this one. In this direction, that is 28.8. Okay. And the third one, we have 0.3 into 104. So according to table, that value is 56.16, right? 56.16. So in this direction, right? In this direction, we'll draw 56.16, right? Now we have drawn all three known. Okay. So we have drawn 6.24, 28.8, and 56.16. So now we are left with 0.96 B2, right? So what we'll do, we'll join the start and the end to complete the coupled polygon. To complete the coupled polygon. Only if it is a complete polygon, then we will have the balancing, right? So we'll complete the coupled polygon. So we from this understand that the angle is going to be this, right? So we can measure this angle, and accordingly you can draw the mass here, right? So this is going to be B2, right? Accordingly, this is B2. So B2, we know the angle is theta 2. So we know we can measure this length, right? We can measure this length. So this length will be equal to 0.96 B2, right? So if this length is 0.92 B2, 0.96 B2, then we can calculate B2 is equal to 57.5 kilogram, right? So 0.96 B2 is equal to vector C dash O dash, right? Vector C dash O dash. From that, we can calculate the CO, no, not the CO, the B2 mass is equal to 57.5 kilogram, right? So now we got the answer of B2, right? So we can replace B2 here, okay? So if you replace B2 there, what we'll be having? We'll be having for B2 57.5, okay? 57.5. Okay, so if you have 57.5 here, you multiply it with 0.6, we will have some answer here, okay? And you will have also some answer here, right? So from here, for your this component is known now, right? 0.6 B2 is known, right? So if you multiply 0.6 with 57.7, I think you will have something around 36 or something, right? So now this component is known 31.2, this is known 36, this is known, this is known, only this component is unknown. So now we are left with only one unknown, right? So now we can draw the force polygon because we have left only with one unknown, right? So now we'll go to the force polygon, right? So similar way, we'll start from OA, right? OA, that is, according to the force polygon, it is 31.2, right? So here 31.2 is in positive direction. So here OA also positive direction, right? OA in this direction 31.2, right? Then we have found this one 0.6 B2, right? So we'll draw that one in this direction. B2 direction is this one. We'll draw 0.6 B2. Since B2 is known, we can have a length for this, right? So accordingly, we have seen, right, theta 2 is the 24 degree, right? So theta 2 is 24 degree. So here your angle theta 2 is 24 degree. So to this line, we have 24 degree. We'll draw this line, okay? And then from B2, now we are going to draw the third line, which is 36, right? So that is 36. So from here, 36 unit, we'll draw the third line in this direction, right? You see here, this and this are parallel. Then what we have is 31.2, right? So we'll draw 31.2 in this direction, right? So this and this are parallel, so we'll draw 31.2 units this direction, okay? Now we are left with only one component, that is 0.6 B1. So now we have to draw this component. So what we'll do, we'll complete this polygon by joining the end of this point and the start of this point. So we'll complete this polygon, right? So if you complete the polygon, that will give you 0.6 B1, right? So if it gives 0.6 B1, what you can do, you can measure this length, right, and apply it in this here. So 0.6 into vector C4 is equal to 34.5, right? So accordingly, your B1 will be equal to 57.5 kilogram, right? So here B1 is also 57.5 kilogram, okay? So based on this, you can find the angle theta 1 also, right? So your theta 1 will be from this line, this theta plus 120. So that is 215. You just have to measure. So which will give you 215 degrees from OA, right? So this is 215 degree from OA, right? So this is the final answer.